Yeah, thank you, Uma. So let me begin by thanking the organizers for inviting me to this wonderful workshop. It's my first time in ICTS, and I really appreciate the fact that I'm listening to so many different talks, and it's been a really wonderful experience and a learning experience. I also apologize that I can't stay for the entire duration, which I would have liked to, and unfortunately, I'll miss on some other talks. Okay, so today what I'm going to talk about is quantum error correction for unresolvable spin systems, with the focus being on this term unresolvable, which I'll try to motivate and also try to, in some sense, explain why this is important. This talk was prepared for a general audience, so for the experts, I apologize if everything seems a bit too simple. I've also left out some of the more technical calculations. So my idea here is to give you a feel for the field and what we are trying to do, and rather than give you more technical details about how things are done. So to begin with, this work was done with my PhD student Harsh Sharma and collaborator Hoi Kun Lau at Simon Fraser University, and the paper is out on arXiv. And Harsh also happens to be a former master student from our under Uma at IIT Palakkad, and he did an amazing job in this paper. Okay, so to begin with, what do I mean by spin ensembles? So spin ensembles are an important part of quantum technology in some sense. It forms a component in what we know as hybrid quantum systems. So if you have computation being performed in superconducting qubits, you also need ensembles which can serve as memory elements, or in itself it can serve as some kind of a computation platform. Interestingly, hybrid quantum systems allow you to allow seamless transfer of information from one component to the other. And if you have error correction code for your computing models, in some sense, you also need to understand how error correction would work if you have these spin ensembles. So to give you an example, an ensemble of spins could be anything from nitrogen vacancy centers to rare earth spin ensembles. It could be trapped ions, or superconducting qubits themselves can serve as an ensemble. So by ensemble here, for mathematical purposes, these are just a collection of non-interacting spin half systems. So the key point of our talk is the notion of unresolvable. So you can think of this as, so I was talking to Sanjukta Roy yesterday from RRI, you can think of a collection of ultra-cold atoms that are trapped. And so these are a bunch of two-level systems which are not dense enough to interact, but they are just a collection of non-interacting two-level systems that are acting there, that are there. You can also have similar setups, rare earth spin ensembles, you can have this, where the notion is you do not really address any of the individual spins, you can only manipulate them collectively. So you can think of a collective light that's talking to them, and the distance between each of the particles is such that the wavelength of the light that you're using to address them will not allow you to, say, target or manipulate any one of these constituents individually. So we are talking of computation and error correction at that particular level. Of course, with such spin ensembles, you would also have local and collective decoherence processes. And so you really need a quantum error correction scheme that can address both the unresolvability and the error issues that come up in these systems. So that is the starting motivation of my talk. So the outline would be, first I will start with a very, very rudimentary introduction to what is quantum error correction. I'll try to tell you the bits and bits and the very basic structure of what error correction is. And through that, I'll try to motivate how we try to apply these to unresolvable spin ensembles. In the second part, I'll try to give you some curious properties of unresolvable states and how you can use those curious properties to finally come up with an error correction code. Okay, so let me begin with what is quantum error correction and the theory of quantum error correction. So in classical world, error correction is primarily achieved through redundancy in some form or the other. So you have bits, zeros and ones, and if you have any encoding, you can just encode a logical 0 and a logical 1 in many zeros and many ones. And if you have some error, you can in principle just measure it. So if you measure a bit, one bit, if it has flipped, it'll become a 0. You change nothing about the structure of the information. You can simply take a majority vote and get back the information that was being transmitted. Of course, yeah, so this is a very rudimentary explanation of how classical error correction is achieved. There are much more complicated ways in which you would do error correction, but majority voting is a fundamental aspect you can always use in classical physics. In quantum world, this becomes a bit tricky because you have the no cloning theorem. So you can't have an arbitrary state and make arbitrary copies of it and then make measurements and take any votes that way, right? That will not work. But what you can do in the quantum world is you can clone orthogonal states, right? You can make many copies of, say, zeros, you can make many copies of ones, and then you can encode the information in something like this. So your orthogonal states, zeros and ones, can be made out of these multiple copies. And now if you have an error in one of the qubits, so you can see this qubit in red has actually flipped, then the ideal case would be to make a measurement and then try to recover the information once you have this measurement. But the question would then come, what kind of a measurement can you make so that the information itself is not destroyed? Because you can't even make arbitrary measurements in a quantum state. Because if you do that, then you'll collapse, and then the information that's basically stored in alpha and beta out here, that's completely lost. So once you have a measurement, you also need to think of how you can recover that particular information. Yeah. Yeah. No. So what I mean by no cloning is you can't clone arbitrary states. I can only clone a pair of orthogonal states. I mean, so I can't have a cloning machine that will give me multiple copies of any arbitrary state. I can always have a cloning machine that will repeat one particular state or an orthogonal state. Yeah. 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 No. So you can clone for alpha equal to 0, and so in this you can clone the orthogonal set. Not any arbitrary alpha and beta. Exactly. You can't have a single machine that will arbitrarily copy for all alpha and beta. So you can have, say, 1 by square root 2, 1 by square root 2, and 1 by square root 2, and minus 1 by square root 2. Those are orthogonal. You can clone those. Yeah. So the idea comes that if you just working with orthogonal states, yeah.
If you can clone the second one, you can't clone any other.
Yeah. So what I'm trying to say is, if you just have orthogonal states, you're basically doing classical computation. It's the non-orthogonalness that introduces quantumness. Okay. Yeah, so let's take at a very simple example. This is the 3-qubit bit flip code. That was one of the first that was analyzed. I can encode the information in, say, alpha 00, beta 11, where alpha and beta is the real information, right? And I can write a simple circuit, which is just a C0 gate, which is just, if you start with alpha 0, beta 1, you'll just copy it to these 2 qubits. Okay, so the redundancy is introduced through a larger Hilbert space here. Say this is an error that's occurring. So you can see that the last qubit has actually flipped, right? And now I can think of measurement protocols that leave the state unchanged. So these are like the stabilizer measurements. So I can make a measurement on this, and without disturbing the state itself, I can detect where the qubit has actually flipped. And you can see, so Z1 and Z2, Z3, and if I start with, okay, yeah, so these are nothing but the stabilizers for this particular code. If you want to understand this in the form of stabilizers, then if you have this additional circuit here for the detection, you can see that the 0 remains unchanged. So Z1 and Z2 does not detect any error, but the 0 flips to 1. So Z2 and Z3 tells you that the last qubit has actually flipped. So if the middle qubit had flipped, both of this would have given you a syndrome. If the first one had flipped, only the first one would have given you a syndrome. So now, looking at 0 and 1, you actually know where the error has taken place. And then you can put some recovery map that will allow you to recover the information back. Okay, so in a very simple case, you can always design a 3-qubit error correction protocol this way. Yeah, H is the Hadamard gate, so it's just converting 0 into 0 plus 1. Okay, so equal superposition is 0 plus 1. You can do the same thing to detect 3-qubit phase flip errors. One thing you should note, this protocol can only detect 1 qubit flip. As soon as you have 2 qubits flipping, this does not work anymore, right? But importantly, this will not work for unresolvable qubits because you actually need to manipulate each of the qubits. Even if I detect an error, I need to touch upon one of the qubits and flip it and then correct it. But if I have a collection in an ensemble, I actually can't really do that. I don't have any mechanism to correct anything, right? So, okay, let's forget this for the time being and let's build onto the theory of quantum error correction. What error correction is actually trying to do is, if I have this initial state and if I have 3 possible errors, which are the 3 qubit flips or 3-bit flips, all of them go to these 3 different states. And if I were to calculate these companies, so these are basically the overlaps between the logical qubits and the logical states, when each of the error has taken place, I see that there is actually no overlap between them. Yeah, so what I'm essentially trying to do is, if my encoding leads to something like this, then this is a poor error correcting code. This will not work. I need my error correction to achieve something like this, where each of the error takes me to some part of the Hilbert space, which is distinctly orthogonal from all the other parts, so that I can detect them, and I can actually apply a recovery map that brings me back to the original state. Yeah? So this is what is termed as Neal-Laflamme conditions. So if you have any system in which you're trying to encode information and study error, you need to ensure that your error actually satisfies the set of Neal-Laflamme conditions, where P is nothing but the projector onto the code space, and alpha ij is nothing but a Hermitian matrix. So all I'm trying to say is, if I have a code space where I'm encoding logical qubits and there is an error, this error should map me to places in the orthogonal, into the Hilbert space that is orthogonal to each other, so that the errors don't confuse me between what had occurred. And this will define what, up to what limit, what different kind of errors you can actually study and correct for. Okay, and this in some sense is one of the fundamental theories of error correction. So regardless of whether you do stabilizer codes or whether you do complicated LDPC codes and stuff like that, you'll also always have to come back and see that Neal-Laflamme conditions are always being satisfied. In this one? Yeah, so this is just a special case for this, but in general it can be, so you can diagonalize this and you'll just get a constant. So there's a basis in which you can diagonalize this Hermitian. Yeah. Okay, so we can also take this to, say, harmonic oscillators or something. So there are a class of codes called the bosonic codes, where you can, instead of encoding the information in these qubits, you can also encode them in some n-level system where you use the energy levels as your to encode the information that you want. For example, if I know that only photon loss is the error that I have, I can encode the logical 0 to be in the even space, even parity space, 0 plus 4, and 1 to be in another even space 2. But if I have a photon loss, this actually takes me to the odd parity state. So you can see if there is a photon loss, it takes me to 3 and 1. And then you can see that the orthogonality conditions are by default satisfied. But again, you'll see that this only works if I'm assuming only a single photon loss. If there are 2 photon losses, then again, you'll go back and there'll be overlaps that can come. Yeah. Again, rudimentary picture, you can go to way more complicated steps. You can define GKP codes in the X and P space. You can define more complicated bosonic codes. For example, if you have photon loss as well as dephasing, you can use a different set of encoding structures as long as, again, you need to satisfy the Neal-Laflamme conditions. Okay, so that in spirit would be how you would go about defining a quantum error correcting code. Okay, so now we want to take this knowledge and we want to see how we can do it for unresolvable spin ensembles. Before that, let us just quickly look at what are the curious properties of unresolvable spin systems and why am I stressing so much on the word unresolvable. So what do I mean by spin ensemble? Again, just a series of two-level systems which are not interacting with each other. It does not depend on what the Hamiltonian or anything is, it's just a collection of two-level systems. And if I were to define a state, I can always define them in their m-half basis. So I can just write this will be plus half and minus half, and I can just put this large vector in front which defines the state for me. Or I can also write it in its total angular momenta basis. Right? I can always write it in terms of its total angular momenta at m. And there's also a degeneracy factor I out here. And you can calculate the degeneracy of this I for every particular j that you have. So to give you an example, if you just have 3 spins, you'll have j 3 by 2 and half. And for j 3 by 2, there is only one degeneracy. So this entire state just has one j 3 by 2. But for j half, you have 2 degeneracies. So you'll get 2 sets of representations which each have total angular momenta half. And these are irreducible representations. So if you prepare the state in any one of these would actually not coherently couple to any other sector. Right? Yeah. So yeah, if it's just a pure states and if you have general dynamics in the systems, this rotational properties will always be followed, right? Okay, so let's look at this closely again. These are, you can explicitly write out what these different states would look like. You can count them for 3 qubits. This actually, total you have 8 states, but then there's a degeneracy out here. So the first part is what is known as the symmetric decay basis because the states are symmetric in this sector. And these are the non-symmetric space. What unresolvability tells you is, okay, this is different j will not form coherences. They are irreducible representations. What unresolvability tells you is, in any experiment, if you can't resolve the spins, there is no way for you to differentiate between the two degenerate j's. So if you're doing any collective operation on this j half will behave identically same for all purposes. So effectively, you can write this entire system by taking this j as a common term, and the density matrix that you actually get is nothing but an identical mixture of all these degenerate states. So the effective dimension of the system for a density matrix, instead of going to 4 to the power n, actually reduces to O n cube, of the order n cube. Okay? And all the states that are defined for j and m, if they have to be permutationally invariant, they essentially have to be mixed states. You can't have a j and m that is actually a pure state, if you need the permutational invariance to be satisfied at all places. But they'll all be identical. Whatever you do, they'll identically transform. So for all purposes, they'll behave like pure states, but they are in principle mixed. Okay, so now you can write this entire sector down in these blocks like this. You have the n by 2 block, n by 2 minus 1, and so on. And, or you can also break them down in pieces this way. And if you are in just doing unitary dynamics or in a closed system, you never jump from any of these. But if you have losses, the losses will allow you to actually move between these structures. Okay, so now, yeah, so this part is so far clear, right? Yeah. 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 No. No, but both is half and minus half, right? So for the J and M, they will just be identical. So you can calculate J square and JZ, but they'll just be identical for all the ensembles. Yeah. So let's go to quantum error correction using unresolvable spin ensemble. So now I want to use this property to define a quantum error correction code. I'll tell you like what people have done so far and why we think what we've done is significantly different. So first, let's look at this ladder again. And let me write down a general master equation for the system. So this general master equation is, there is some Hamiltonian that describes the dynamics of the system. Then you have the different kind of losses. So you have a bunch of collective losses and you have a bunch of individual losses. But again, these individual losses do not really target anything. You still don't know there's an individual loss, but from which qubit it is. So what does a collective emission does? A collective emission will only move you up within the same ladder. If you have a collective pumping, again, that moves you within the same ladder. If you have a collective dephasing, that just keeps you in the same level as it is. So this is very interesting. So now if you're doing error correction just with collective losses, you actually don't even need to consider any of the other geometry. You just need to choose one particular J and you can just encode all your information. So most people choose the Dickey basis and just work with the Dickey basis because all your losses will just make you move along the Dickey basis. And that you can work with a much smaller dimension than it is. But you see, yeah, collective losses keep change. So most QEC codes that you'll see are within the collective states are limited to this particular basis. There are a lot of advantages. All the states here are actually pure and not mixed. You can encode it. All the losses will just make you move within this. You get a perfectly nice code. But what happens is, as soon as you have local emission, you can actually go to different Js. And this is unavoidable. You can't really have a system in which you just say, okay, I have collective losses and nothing else. So as soon as you have this, then your entire structure where you just started with these pure states, this doesn't work anymore. Again, if you have a local pumping, this can actually take you to different Js. And local dephasing keeps you for the same M, but allows you to move within the J. So now you need a structure that actually involves even the smaller values of J, and you need to go to the space that is essentially mixed and encode your information there. Because if you start with the pure state encoding, if it goes to the mixed, there's no way you can recover that information back because the structure is completely different. So local losses will change J. Yeah, but they are integral to the spin ensemble dynamics. So now what we want to do is, as we mentioned, addressing individual spins is practically challenging. There are some QEC protocols that try to implement this, but they always go back to addressing individual spins for the recovery part. So they say, okay, let me allow individual losses, but they'll also say, then you have to allow me to do individual spin addressing to correct them. So we want to avoid that. We say that's not possible. So you have individual losses, but can you only use collective protocols to actually encode as well as recover the information, right? So how do we go about it? We try to encode, say, any general d-dimensional information, any qubit, in the any particular J space, and we use the mixed state description to actually do it. So we have any qubit that you can define in this entire specific ladder, and then with using the qubit, I can define a logical qubit. Say I choose psi L to be some 0 and 1, where this 0 and 1 can be any combination of these M levels in any particular state. And then what I do is I ask the Néel-Laflamme conditions to be satisfied. So I ask now if I have the entire set of errors that I chose from the Lindbladian, what would my Néel-Laflamme conditions look like? And the Néel-Laflamme conditions say, okay, the simplest example. So you can use the Néel-Laflamme conditions and these set of encoding to look at any kind of error that you want. So we just look at a simple example. Say we have a simple example in which there is a single error, but it can be any one of these errors, but only a single error. And say we just assume we'll use 4 levels to do the encoding. Then the Néel-Laflamme conditions tell you, okay, that's fine. Just make sure that these are the relations that you satisfy between the different M1s and M2s that you're taking to encode the qubit. Right? So now you can, so if you have M1 and M2 satisfying this relation, you'll see that you'll need a minimum of 9 qubits or 9 levels to actually encode the entire thing. So if J, there is a threshold of 9/2, if it goes below this, you can't actually define the encoding. And you can see that there are enough level spacings in between, which allows that if you have a loss, you should not overlap with each other. You can still be orthogonal to each other. If you have more losses, you'll need more spacing between the encoding. Yeah, but you can generalize this to any kind of errors that you want to study. Fine, so we encode this in any logical J space, and then you can theoretically show what would be the action of any particular loss in the encoded state that you have. So supposing if I have collective losses, which I can represent by some general gamma m, you can calculate the coefficients of how this transition will take place if you're from one point in the invariant space to the other point in the invariant state. So you can actually calculate what the transformations are. So this is just tedious algebra, yeah, so worked out by my PhD student, but it consistently, you can derive all these terms. Similarly, you can also define it for the local losses. So these are terms that you already can calculate and you have at your disposal, which you can then implement while trying to, say, simulate the entire dynamics of an error taking place in a circuit. Okay, yeah. So they are mixed, but they behave like code states because you can't resolve them. So it's like writing a set of pure states with all equal probability, and they all rotate identically. Yeah, sorry? Yeah, so I'm just writing it as a logical pure state. Okay, so let's see how the protocol would then go. Supposing I have alpha and alpha 1 that I want to actually encode in the logical qubit, I can choose a series of these levels, M1, M2, minus M2, minus M1. And if this logical state, the choice of M1 and M2 would allow me to encode the information. If I have some random loss, say individual decay, the state will actually end up here in some J-1. Let's assume it ends up in J-1. It could have also gone to J+1. But I can do a phase estimation of the Jz square and the J square and the Jz square, which will tell me if I started with any particular value of J, whether I ended up in J-1 or whether I ended up in J+1. These are collective operations. It can also give me an estimate of what the M values were once the error took place. And then I can map a recovery Hamiltonian that would actually take it back to the original position. Sorry, and another map that would give me back the original encoding again. Again, you can do it collectively. Now what you'll observe is, even though I've gone from J to J-1, the information itself is intact. I don't need to go back to the original J. As long as alpha and beta are protected, I actually don't need to. There is no collective process that will allow me to go back to the original J. But I don't need to go back to the original J. I can protect the information that was encoded. I just need to readjust it in the new levels. Right? So again, now I can decode it here and get back what the original information was. So one way to look at it is, let's take an example of n equal to 20, where j is equal to 10, and I have chosen the levels m2, minus 2, minus 5 for my encoding. And then I run a series of trajectories to see what kind of error takes place, and I try to study them. So if there is no encoding, I can see that there are different ways in which the losses take place. If the state is completely unencoded, it actually has it falls off actually quite slowly. But the reason it falls off quite slowly is because I've taken the lowest energy level, so there are barely any losses in that. But if I just take this encoded state without any protection, this actually drops off quite quickly, right? But if there is an error correction that I can apply, then you'll have this black line. And if I can do an error correction along with some additional protocols, I actually get this green line on the top. I'll tell you what the additional protections are, where you can see that the fidelity of the initial information is completely protected. So if I have an initial qubit that transferred the information to this ensemble, and if I run various trajectories to simulate the open system, I can still use this error correction protocol to keep that information intact. Okay, so the reason this is low is because, yeah, these are low excitation states. So yeah, encoded state, you have more excitations. Yeah, so after multiple rounds of decay, you can actually get this red line out here. But what happens is the black line actually drops because you reach the threshold and you can't actually do any more error correction. But if you use a teleportation-based extraction, so whenever you reach the threshold, if you transfer the information somehow to a higher J model and repeat the entire protocol, you'll see that the error correction protocol actually works. So this threshold is, so for numerical reasons, we just took n equal to 20 to j equal to 10. You can actually take it to a much higher j so that the threshold is not reached for quite some time. Okay, so how much time do I have? Okay, I still have 9. So in principle, yeah, this is more or less what the protocol would do. And you can see that for different kind of errors, you can actually repeat this entire protocol again, and you can see for, again, these are like running averages over many quantum trajectories that were run for different kind of errors. But the only thing that you have to keep in mind is this is under the assumption that you only have a single error at any given time. There are no two errors. So if you want to study, say, if you have two single errors, one after the other, or if you have one dephasing and one collective loss, then you'll have to go back to the original Neal-Laflamme conditions and find a different set of levels to actually encode the information. Okay, so I think this is more or less the talk that I had in mind. So we wanted to come up with a quantum error correction code for spin ensemble systems that essentially cannot be resolved. Again, by resolved, I mean you cannot use a technique in which you can individually address any of the spins. So you can't encode information in a specific spin and correct it in a specific manner. And we really want to store the information in this permutationally invariant states or the collective states of the systems, such that even though they are generally mixed, that allows the entire information to flow throughout the series of angular momenta values that you have, rather than just a fixed angular momenta value. And you can actually protect against all prominent errors that you see in these kind of ensembles. You can, in fact, even one question that people ask is, if you have these collective systems, one major error is when the atoms themselves disappear from the lattice or something. But you can show that even in those cases, detecting the J will allow you to estimate whether a spin loss or a complete loss of a emitter has taken place, and then you can do a collective correction to get back the original information. Yeah, so our recovery process does not require resolving any subset of spins. And the formalism can actually be extended to do quantum sensing protocols, quantum memory protocols, and among other things, which I did not touch upon in this talk. Yeah, with that, yeah, thank you.
Any questions?
Yeah, so this goes back to what Srijit and so on were asking. So
Yeah.
the initial information that you would like to encode is itself of the ensemble nature. In the sense, it is already a mixed state, is it? Like, are you just encoding an ensemble into an ensemble?
No. So, yeah, so there is a second part to this study, which says that supposing I have alpha 0 and beta 1, how can I engineer and take the state to one of these ensembles and encode it there? So you can prepare a superposition in the ensemble, and this information could have come from any other part of the circuit. It could be from a superconducting qubit or a photon which was carrying the information.
Okay, so then I'm still confused about the pure state to the mixed state part. So whether your encoding process itself, in a sense, is noisy in some sense.
Yeah, so it's actually not noisy. What happens is, since the entire process is collective, even if I'm trying to change just one J and M, the entire set of J and M will identically change. There is no way they can behave differently. So it would be like, so if psi is some superposition of, or let me write it, some superposition of some J Mi, so this is what I want to achieve, right? But in reality, the state is more like psi with all the i's, something like this, 1 by ADI. But since this mixture can't change in any behavior, it's just like many copies of the same J just changing at the same time.
Okay, yeah, maybe we should discuss offline.
Yeah.
Questions?
Can you elaborate when you said that the state is actually a mixed state, but it behaves like a pure state effectively? What did you exactly
Yeah,
mean?
so something like this. So in principle, this mixture, so all the information is actually captured in the psi itself, right? But the psi itself, so whenever you're doing any collective operation, you can think of it as a pure state that is evolving in time or whatever is happening. It's just that at every given moment, so this is true for all the degeneracies. So at any given moment is just an equal mixture of all these degeneracies. So I can just work with one of the degeneracies and I'll know what's happening to everyone else.
I see. But that's when you only have what you call these non-local or global losses, right? Because
no, even in anything, that will be protected throughout the system. Because every J has its own degeneracy. So even if you go to the other one, it'll just pass on to the other set of J.
Oh, I see. Okay.
Sorry, I have a related question. Does this imply that you are assuming that your decay, the single spin decay rate is the same for all the spins or not?
Yeah. So
okay, because otherwise you go out.
Otherwise it's an individual process. Okay. The computational invariance will be broken. Yeah.
Can I think of this as some kind of super selection rule that forces you to be in a certain subspace? In which case, can I not look at this as a kind of decoherence-free subspace of some form, or even maybe a more active form of a DFS, but not a passive?
Yeah, so I think decoherence-free subspaces arise as soon as this I disappears and you actually have, so for instance, if there is a little inhomogeneity in the system, you'd get rise to a lot of these decoherence-free subspaces. Okay. So this is one of the major issue is the fact that I'm saying all of them are identical, how physically relevant that is, because there could be some inhomogeneity in the system which will actually break this entire thing. So we are trying to look at codes which can tolerate some amount of inhomogeneity in the system.
Try to understand once more. So you had shown this two brown states, which were, I assume the logical one is some mixture of the two, what you call M1 and minus M1, is that correct?
Yeah, no, they are actually superpositions of that.
Oh, superpositions.
Yeah. So for any J, I will get some superposition of the M levels. Some of them will be 0 and some of them will be 1. But the whole J as a whole will have degeneracies. They're identical J's sitting there. It's just that we don't need to worry about them.
Taking, let's say, M1 and minus M1 as the code word.
True, but you would end up with some errors which you can't correct. In principle, you can do that too. You mean like just take the cat states on the top, right? Yeah. Then the Neal-Laflamme conditions, you'll need to be careful about what kind of errors. There are a lot of errors for which you have simpler codes that are more robust. But this seems to be a bit more general, like I can do it over a lot of different kind of processes.
No more questions? If none, so let me thank Himadri for this nice talk.